Good afternoon, respected panel. Today we're representing Group 21, the final group. I'm Joel Thompson and this is Saeed Farshi. And we're going to talk about our project, which is designing super-oleophobic surfaces for touchscreen applications. So touchscreens are everywhere these days. They're so pervasive in today's society, in every household, from children to seniors, from cell phones to laptops to computers and even eventually maybe televisions. They're everywhere, and they're definitely here to stay, I would say. And we see the main problem with this is that they have fingerprint smudges as we continue to use them, and they tend to accumulate dirt. This can reduce the sensitivity and functionality, and also it reduces the aesthetic appeal of the device. To combat this issue, current products that are offered, you have some spray coating or liquid applications. They have for various Apple products and such. You have the film protector, the plastic film protector, and as well, Apple and BlackBerry boast to have a built-in fingerprint display as well. But looking deeper, you see that the spray coating applications, they're not ideal because they would need to take time to dry and frequent applications, and they don't fully remove the smudges. With the plastic protectors, in trying to put them, they're susceptible to forming bubbles underneath, and that's also not ideal, and they could be susceptible to scratches as well. And the built-in fingerprint feature has not been fully realized, because customers have increasingly given negative reviews saying that it's not really there, if at all, and it disappears after a couple of uses. So what do we propose? Having a nanostructure textured surface coated with an oleophobic material. So we take our inspiration from, of course, nature's herself, famous self-cleaning mechanism, the lotus leaf, where it has hierarchical pillared structures, waxy structures, that are able to prevent water droplets from wetting the surface, and they take out any dirt particulates as they roll off the petal. So in trying to mimic this design, researchers have come up with various models to try and understand this phenomenon. There's the Cassie-Baxter model and the Wenzel model. The Cassie-Baxter is the ideal model where you have the air pockets in between the pillars supporting the droplet, and giving that true greater than 150-degree contact angle, as you can see on that picture. And that's what we really need. And the Wenzel state, the fluid penetrates in between the microstructures, and the contact angle is lower. And that is, even though gives some degree of hydrophobicity or oleophobicity, is not the maximum achievable. And there's a critical pitch distance, or the distance between the pillars, that where you transition from one state to the other. So our design goals are to have a oil-water repellency that is transparent and durable for the usage of the device, and ultimately potentially integrated into the device as well. Now I'll pass it on to Saeed to talk about the fabrication.
So in order for us to achieve these these goals, we need to go through a series of fabrication processes. So what we did at the beginning was that we had to create these nanopillars on top of our glass substrate. And then in order to protect those nanopillars from breaking off and to add an extra support, we decided to deposit several layers of cellulose nanocrystals, or CNCs. And finally, to reinforce the hydrophobicity of the surface, we're going to treat the surface with a low surface energy material at the end. So moving forward to the fabrication, excuse me, in order to create these nanopillars, initially we created a mask. So we went through a series of techniques that were done in the clean room. After the mask was created, we started with clean blank wafers, glass wafers. We did clean the wafers with the RCA cleaning technique, and then we deposited a layer of silicon dioxide on top of our glass substrate. We are using the mask and photolithography techniques. We transferred the design from the mask to the glass substrate. We exposed and developed the surface, and then finally, using the reactive ion etching process, we created our nano pillars. And at the end, we stripped off the photoresist from the surface. The next step was to deposit the CNC or cellulose nanocrystals on top of our nano structures. We did that using electrostatic layer by layer deposition, in which will allow us to have several layers of these crystals on top of one another. So using the PEI, which sustains a positive charge, and knowing that our CNCs are previously functionalized with carboxylic groups, which are negatively charged, we deposited CNCs up to 5 layers on top of our glass substrate, and at the end we were able to wash the surface off. The next step was to reinforce the hydrophobicity of the surface. We introduced a very low surface energy material, a slate material which has a long carbon chain with fluorines attached to it. It was a dip coating process, and we did that for several times until the surface was fully coated with the selenium compound. Now we have to go back and check whether our design meets the customer requirements or the hypothesis that we made at the beginning. So we need to do the we need to take surface images to make sure that our nanopillars are there. Later on, we have to do the contact angle measurement to see how our sample, how our surface reacts in terms of when it's in contact with oil or water. And at the end, doing some mechanical testing and quality testing to make sure that the sample doesn't veer off, and also it's transparent to the light. So moving forward, this is just an optical microscope image just to have an idea of how the surface will look like. But if you go, if we move basically a little bit closer, we can see exactly the nanopillars that we designed and we fabricated on the surface of the glass. They're about half a micron in length, and then the diameter of them are about like 3 to 4 micrometer, and the periodic distance between the pillars are about 5 micrometer. The picture on the right shows just the one pillar by itself and how it's basically attached to the surface. The next, so now that we know that we have our nano pattern design on the surface, we needed to make sure that we were able to achieve a high contact angle when the water droplet or when the oil droplet is placed on the surface. The picture on the left shows a modified surface, a patterned surface, and the picture on the right is just a glass substrate. As you can see, we're able to obtain up to 151 degrees of contact angle, as opposed to the picture on the right, which gives us a maximum of 20 to 30 degrees of contact angle. So the water basically flows on the regular surface, as opposed to our surface where the water forms a droplet with hopefully an air packet underneath it. We did the same test with oil. As you know, oil has a lower surface tension, so it's easier for it to flow on the surface. We were able to obtain up to 80 degree contact angle with oil. The picture on the right shows an oil droplet on a plain glass substrate where it gives us a contact angle of very low, I think about like 20 degrees. We did this test for several different samples, and the average that we got for water droplet was 134. the industry standard for a hydrophobic surface is about 150, so we're very, very close to the to what's expected. And for oil droplet, it's about 80 degrees, which is very close to 90 degree. That is the limit for repellency of a droplet from the surface. At the end, we need to make sure that our design is stable for uses over time, since the customers are going to be using this over and over for a longer period of time. One of the industry standard tests is the mechanical rubbing test, where you use a dry cloth and rub the surface for as many times until you see deterioration in its properties. We went away up to 1,000 rubs without seeing any changes in the oleophobicity or hydrophobicity of the surface that we had. Same goes for the transparency. So since we're going to use this as the final glass substrate on the display of the device, it needs to be 100% transparent without any light diffraction or anything. And as you can see, but just by the visual inspection, we can see that the wafer, the design wafer, is able to transmit light without any problems. So going back to our previous goals that we set at the beginning, we can see that our oil and water resistance goal was fully achieved. Our transparency is achieved completely. The second goal that we had was durability, which was achieved to the point of 1,000 rubs, as was previously described in the test. And then the last goal that we had was to implement this on an actual surface of a device, such as a cell phone display or a touchscreen display, which we weren't able to do that yet. And moving forward, these are the next steps that we're planning to take. Is the first thing to do is to try to implement our design, our wafer, on a bigger scale, and to put it on an actual device to see how the customer, the reaction, or basically how it will work for us. We also need to optimize the hydrophobicity of the surface by changing the pillar size or the distance between the pillars. Due to time constraints, we weren't able to change our design for so many times, but there is still space there for us to go there and try to optimize our final design. And these are references. And at the end, thank you for listening, and if there are any questions, I'd be happy to answer.
Questions? So I have a question. So this you compared one with this treatment, the other one without treatment, this contact angle. So on the left side, that one is a pattern with another patterning, or just
the left one is a glass substrate which is patterned, so there are nano pillars on it. And then it is also
with the
chemical
modification.
Exactly.
Yes.
On the right side is
nothing.
flat.
Just the glass.
So did you compare, the glass with the nano patterning, but without this siding, like a floral siding modification?
We didn't do the contact angle measurement, but we just by dropping the droplets on the surface, you can see the degree to which the surface is hydrophobic. So let's say for the picture on the right, as soon as you put a droplet on the surface, it will form a bubble, and it clearly shows that your surface is like super hydrophobic. When you have the patterned surface without the surface treatment, it will create the water won't roll off the surface. It will stay at its own place, but it won't create a whole full bubble.
So it's still not, it doesn't wet that much, but it's not complete. Yeah.
So also, did you compare, yours with the one just flat surface modified with this
silane? Yeah, we one of the wafers we had it didn't etch properly. There was no etching, so I guess we tried it, and it was less than the one that we saw with the pattern.
Because my concern is you say it's nano, so like lotus, whatever, that because the nano structure, But
Yes.
yours is like a pretty big micron, right? I don't know that.
Yeah, I think it's,
effective or not.
yeah, it's like the deposition, I mean the fabrication constraints, like with the lab that we had access to.
I just
So,
want to decouple your like nano structure effect.
Yeah.
And also there's a chemical modification effect. Which ones don't like more don't?
Yeah, I do believe that the chemical modification had a bigger chunk of the work, but the constraint that we had was with the clean room. It was so hard because we're undergrad students and we don't have access to the clean room.
so like if we could do electron beam lithography, then we could have like better aspect ratio.
This was the best ratio that we could have got with the with what the department was allowing us to work with to obtain these resolutions.
So that leads me to, I guess, the next question, and that's in terms of the processing and cost of this processing. It's not one of the cheapest, methods that you would have for some kind of larger scale.
Like actually,
Apple does this very similar process. Very, very similar process.
That's right, but Apple has billions of dollars in cash.
So the biggest cost is the mask.
Right. I could imagine that. Yes.
And the mask, you can use it for 1 million times, over and over again. So basically, the more wafers you create, your overall cost will be lower because of the math. Or and if you have the clean room built in, or if you have the access to the clean room for any company, it's pretty feasible for them since they're not needing. They don't need any.
No, I like that. But here's the question: you guys wouldn't envision selling the actual phone with this sort of
No,
you would basically make the coatings on some kind of substrate that would then be, I assume, somehow attached or added to a device.
Exactly. So the phone companies, the display has like several layers after the capacitor, and the last layer is just a glass layer, which we're trying to focus on that.
Right.
So they go to outside vendors. Right now they're going to the glass companies, just a regular glass, to buy it off and then put it on the surface. So what we're trying to do is we're trying to convince these manufacturers to come for our glass, which is
treated.
able to, which is a
But that's
self-cleaning
exactly what I'm saying. I mean, when the company produces the phone, the coating is should be a marginal cost for them.
Yes.
And if you're dealing only with one, basically layer, one coating, on top of all of this, you should do something that costs sense, basically, in order to be compatible with the overall cost of a device. So that's that sort of cost structure is, given the methodology that you're using, is something that I'm bringing up, as
No, that makes sense. Yeah, perfectly makes sense.
Sorry, I didn't hear that answer. What did
Oh,
you
I
say?
said that makes sense. Yeah, it does make sense that the costs are. Well, this is more of a it was more of a research project for us.
No, I understand that. If you
But I
think
mean,
about
we
that,
could
that's-
batch process the
I
wafers
think
though.
If I reiterate, that's more in a manufacturing stage. That's not something you're going to spray on later on yet once you purchase the phone. Is that correct?
Yeah, the having the coating itself should be at the manufacturing stage. Like you could batch process it, like because it's dipping it into the oleophobic coating.
Right.
So
And then it's meant to last.
Yeah.
Right? It's not later on. you
No.
spray on it.
it's meant to last.
Okay, I think that's the end of the day. Let's thank you for everyone. Okay. And have a nice weekend.